Chapter 10, Lesson 1. In this lesson we'll speak about gases, a very important state of matter, and studying gases will allow us to understand a lot of interesting information about any substance, essentially. So, in general, gases, unlike liquids and solids, will expand to fill their containers. They are highly compressible and have extremely low densities. And this is all owing to the fact that gases are much less dense, or gas particles are much further apart than their liquid or solid counterparts. You may know that between solids and liquids, how close the particles are together are about pretty close. But then gases are much farther apart. So there's a huge difference here between liquids and gases. Roughly, gases are about 1,000 times less dense than liquids, which means the gas particles are about 1,000 times further apart from one another than liquids. Solids and liquids, comparatively, are very similar. The density, for example, of solid water is very close to 1. The density of liquid water is very close to 1. The density of gaseous water is much less, 1,000th, essentially, of a gram per liter. And we'll use this idea to explain many of the properties of gases. Let's take a look at something called the kinetic molecular theory. Technically, we're going to put forth some statements about gases, which will allow us to talk in more detail about gas behavior. The first tenet, or the first a tenet essentially is a statement or an idea about gases. Is that the first one is that gases consist of a large number of molecules that are in continuous random motion. So there's really no order to the way these gas particles move, and inside this container they're constantly, you can say, moving around, bouncing off the walls. This is essentially the picture here that we try to depict, randomly in all directions, all over the place. Tenet number 2 is that gas particles or molecules don't take up any space. What this means is that the gas molecules themselves are so tiny compared to the overall container in which they are that we can essentially ignore their volumes. Their volumes don't really add much to the volume of the container. We can essentially assume that the container is empty in a way. And that's kind of the idea. Tenet number 3, there are no attractive and repulsive forces between gas molecules. And again, technically they exist. These attractive and repulsive forces exist, but gas particles move so quickly that these are not noticed, is kind of the idea. And if there were repulsive and attractive forces between particles, then what you would have is you would have a liquid. If these were to attract one another, technically they would condense into a liquid and then into a gas. So liquids, and then into a solid. Liquids and solids definitely have strong attractive forces between their molecules. Gases don't. Number 4, collisions between gas particles are elastic. This word elastic means the energy is conserved. So here it says the energy can be transferred between molecules during individual collisions, but the overall energy of the molecules do not change. And this is strange but true. So gas particles essentially never stop moving. If you have a bunch of gas particles in a beaker or a container, these gas particles will never stop moving. They'll constantly keep moving, and one gas particle can collide with another, transferring its energy, but the total energy does not get lost. This is different than on our macro level, where if you throw a ball at another ball, eventually the energy that this ball number 1 transfers to ball number 2 will eventually get dissipated. But with gas particles, it is not so. And then finally, number 5, the average kinetic energy of the molecules is proportional to the absolute temperature. And the idea here is that temperature roughly is a measure of molecular motion, molecular speeds, and really the energy in general. So this is a worthwhile graph to take a look at and have some understanding of what this is talking about. This is essentially a graph from statistics, and the mathematics of statistics essentially is applied to very, very large populations. In any sample of a gas, you have literally billions and trillions of gas particles, and we have to apply. We can't really talk about the velocity or the speed of an individual gas particle. We have to talk about them in terms of the whole system, the whole population, and that's if you're taking statistics or if you've heard of it, you get what's called a bell curve. So this bell curve essentially shows you that most of the molecules have an average energy. This essentially is kind of the middle of the bell curve, and this is the middle of the bell curve for the blue. And a few gas particles have very low energy. Very few are in this. A few have very high energy, but most of the particles contain an average amount of energy. Now, the red versus blue here, you'll take a look. The red is at a higher temperature, so what happens as the temperature goes up of the particles, more of the particles have a higher speed. Down here we have molecular speed, so the proportion of molecules that have a higher speed increases. So if you shade that here with the red versus if I shade it with the blue, you'll see that there is more red than there is blue, essentially. And that's kind of the idea. The proportion of molecules having a greater speed increases. In general, if you want to think of this as it's simply temperature is directly proportional to the speed of the molecules, that would be sufficient for now. So we can ask a question like this. Suppose we have a gas confined to a cylinder. So here's our cylinder. What will happen to the pressure of the gas inside the cylinder if, first of all, we cool the gas from 298 Kelvin to 260 Kelvin. Recall we will use Kelvin for the temperature, and if you forgot to convert from degrees Celsius to Kelvin, you would add 273, and you'll get to Kelvin. And this is because absolute zero technically is negative 273. It's 273.15 to be exact, but 273 will suffice for our calculations here. We have to use Kelvin because it is an absolute temperature scale. It does not have any negative values. We'll always have to use Kelvin when working with gas substances and calculating the pressures and the like. So if we cool the gas from 298, which is roughly room temperature, down to 260, which is essentially below zero, what will happen to the pressure? Well, as we cool a gas, the particles start traveling slower. So we got a bunch of gas particles essentially in here, whizzing around and enjoying a good time, flying in all different directions. As they slow down, because the temperature went down, the pressure goes down. Then they don't apply as much force to the walls of the container, and therefore the amount of pressure in the container goes down. For B, so for A we can say pressure decreases is the idea. What if we move the piston to reduce the volume of the gas from 1 liter to 0.5 liters? So we'll say that this is exactly 1 liter, 1L, and right here is 0.5 liters. So say we move this piston down to where the 0.5 liter mark is. And so all the rest of this essentially is closed off. What will happen is the molecules will be forced together, so the amount of collisions on the container now increases because we have more molecules and they have to be colliding as they were up there. Because the number of collisions increase, the pressure will also increase. So for B, the pressure also goes up. And technically because, again, the number of collisions increase. And then see what if we inject some additional gas to the gas inlet valve. So if we put a bunch of gas through here, obviously what we're doing is we're increasing how many gas particles we have. So if we increase how many gas particles we have, the amount of collisions also increases, and this increases the pressure. So the pressure again increases. So this, if we understand gas particles as little molecules that essentially bounce around very quickly, randomly, we can predict the effects. And these are more intuitive, logical effects that you can probably come away with without even knowing the specifics here. Okay, next we'll talk about pressure. Now, in general, the equation for pressure is given here. Pressure is F over A. Now, F is force, and A is area. So, if you were, say, to stand on one foot, say if you had, here's your shoe. This shoe isn't very. So here's a walking shoe, a little better. If you were to stand on one shoe, you can calculate how much pressure you're applying to the ground. What you'll have to calculate is the surface area of your shoe, and the force technically will be your weight in pounds. And this will allow you to, if you divide the two numbers, this will allow you to calculate how much force you're putting on the ground. Now, if you're a young lady and you wear high heels, and or if you're not a young lady and you still wear high heels, if you put all your force on the high heel, what will happen is your area would have gone down. So the same force is placed in a smaller area and the pressure shoots up. So this is why if you put a heel through soft ground or something, the heel goes right through, because the amount of pressure has increased. And this is a general explanation of pressure. Now, how pressure applies to gases is you can think of something called atmospheric pressure. So the pressure that we feel from the atmosphere that is above the Earth. And this pressure technically is defined as the area of 1 meter squared, 1 meter by 1 meter, and then all the mass of the air above us, which is quite a bit. This is 10,000 kg, or 10 tons. That's quite a bit. 10 tons of air on 1 square meter of ground, which is pretty intense. The amount of pressure, atmospheric pressure all around us is pretty high. And there are some experiments you can do to prove this, but it is pretty impressive. Here are the pressure units, the common pressure units at sea level. And we have to specify at sea level because altitude will change the pressure. So the most common unit is probably PSI, pounds per square inch. This is what you use to fill up your tires. Atmospheres are used by chemists in general. PA is pascals, named after Blaise Pascal. Blaise Pascal, a famous mathematician, Pascal, and scientist. And kPa again is kilopascals, just divided by 1,000. 760 mmHg is a very famous one. This came from the first measurement by a chemist of pressure, and essentially it's the amount of volume, 760 millimeters of liquid mercury, that will be held up by the atmosphere. So if you look up Torricelli, you'll find out how he designed the first barometer, the first measure of pressure, and in his honor we'll call this 760 torr. All of these are equivalent. Here are some other conversions. If you want to go, the bar is actually very similar to the atmosphere, but not exactly the same. Bars are used in some other areas of science, and it's related to the pascals. This is essentially 100,000 pascals, or 100 kilopascals, is equal to a bar. So these are all the pressures at sea level. All the different, just like there's different ways of talking about mass, kilograms, pounds, ounces. There are different ways of talking about pressure. Here is the barometer. Here's where the idea of pressure came. It's worthwhile to understand what the Torricelli barometer is all about. So what the early chemists did is they took a glass tube and they filled it completely with mercury. And then they inverted it into a pool, a container of mercury, and to their surprise or delight, the mercury stayed up. Most of the mercury stayed up in the tube. And this was about 760 millimeters. This is essentially a meter-long tube. Think of a meter stick. 760 millimeters of mercury stayed up. And this was... it's pretty heavy, and the mercury is one of the densest materials, about 13 grams per milliliter, extremely dense. So the amount of force from the atmosphere holding up the mercury was intense, was very, very high. And this essentially experiment opened up to the scientists, the chemists, how much pressure there is around us. And enormous amount of pressure, really. And the guy that is credited for doing this is Mr. Evangelista Torricelli. So why don't we do some conversions here as just an exercise in dimensional analysis. So we want to convert from 1.1 atmospheres to torrs and then to bars. So why don't we do to torrs first? Like doing any other conversion, let's go ahead and begin with 1.1 ATM. We want to multiply by a conversion factor. In this case, we'll put atmospheres on the bottom. We'll put Torricellis on top. And according to our previous slide, if you take a look, an atmosphere is 760 millimeters of mercury. This is our conversion factor. So we'll put an atmosphere down below, 760 Torricellis up above, and then grab your calculator, and 760 times 1.1 gives us a fine value of 836. Being that we have two sig figs, why don't we put it to 840 torrs, 840 Torricellis. No decimal place to make sure we follow the two significant figures. Let's go ahead and take this now to bars. Now the bar is actually related to us here. A bar is 10 to the 5th pascals, and then pascals are related to Torricellis. So this is going to be our plan. We'll first go from Torricellis to pascals, then from pascals to bars. That's 101,325 pascals. So we could technically begin with atmospheres. It's probably wiser to begin with atmospheres, but let's go ahead and begin with our 840 Torricellis, because we did round 840, and that's what may introduce a little bit of error. Not this will mess us up by too much. So let's go first from Torricellis to pascals, and 760 Torricellis based on the conversion factor is 325 pascals, and then we'll go from pascals to bars, and a bar is 10 to the 5th, or essentially 100,000 pascals. So if you do this calculation, we get 840 times 101,325 divided by 760 divided by 100,000. And we should get ourselves 1.1, doing significant figures, 1.1 bars. Now, this is done on purpose, actually. This is to show you that, in general, bars and atmospheres are equivalent. If you take it out to 3 or 4 significant figures, you'll see a difference, but bars and atmospheres are about the same, is the idea. So make sure you do a little conversion between these units. Let's take a look at something called a manometer. Now this is a device that's actually used to open or to measure the pressure of a gas. So what we do is we put the gas inside a vessel of sorts, and then that vessel is connected to a tube which traditionally, again, has mercury in it. And this is actually Hg, good old mercury. And the pressure of the gas, technically if there is no gas, you could say the mercury, well, if the pressure, if these lines were, let's think of it this way, if these two lines right here are on the same level, what this means is that the pressure of the gas is equal to the pressure of the atmosphere, if these were essentially equaled out. If you had a picture essentially that looked like this, if the mercury was looking like this, this means that the pressure going in here and the pressure going in here from the gas are equal. Now, if the mercury level if you take a look here, the gas looks like it's winning. In other words, it's pushing the mercury further down, and the difference is the height. So what happens is the gas is winning by this much, so the pressure of the gas is the pressure of the mercury plus this height, and that's what this equation says. If the opposite were true, if you had a situation where you have a higher level here and a lower level here, then you can say that the mercury is actually winning, and then you'll have to take this height and subtract the height from the atmospheric pressure, because when they're equal, the pressure of the atmosphere equals the pressure of the gas. And hopefully we can do a few examples of this as it comes to it. And then finally, let's mention something called standard temperature and pressure in this first lesson. And these are a set of conditions that the scientists have agreed upon to use, or chemists have agreed upon, when discussing gases. And this is defined as 0 degrees Celsius, at 273 Kelvin, in other words, and 1 atmosphere of pressure. And essentially this is called STP, standard temperature and pressure. And this is a worthwhile conversion factor here. We'll actually use this and we'll dry this. We'll show you where this came from. But a mole of any gas at STP, meaning at 0 degrees Celsius and 1 atmosphere of pressure, occupies about 22.4 liters. Now this is a pretty high amount. If you think about your 2-liter bottles of, say, Mountain Dew, so essentially this bottle is about 2 liters, so you got yourself 10 of these essentially lined up, and that's how much a mole of gas occupies. So keep going when you have, until you have 10 of them, to kind of visualize how much this is. So a mole of gas, which isn't that much, occupies 22.4 liters, quite a bit of volume. And this concludes our first lesson of Chapter 10.